Okay, so section 5.2 is on verifying identities. So verifying an identity means proving the identity. So in effect, what we're going to be writing today are just a bunch of little proofs of the various identities we're going to see. So really, this is a situation where the best way to explain how to do this is to really go right into an example. So let's start with an example. All right, so here is a trigonometric identity. Now, this is not a fundamental identity, but what we are going to do is verify that indeed this is an identity. And the way we do that is by choosing one side to work with, and you want to choose the more complicated looking side. So in this case, I would argue that's the left-hand side. And then through the act of simplifying or using identities that you do know, try to arrive at the right-hand side. So let's see, we're going to start here with the left-hand side because it is the more complex looking side. And the first thing we do is we simply write down that left-hand side. Okay, now at no point are we going to write down that this is equal to the right-hand side. Okay, we are writing a proof, which means we are only allowed to write down things that are obvious. And this is not obvious yet. In fact, it's what we're trying to prove. All right, so once you've written down the left-hand side or the right-hand side, if you choose to start with that side, then think of the job as just simplifying the expression. So what could we do with this thing? Well, we could distribute the secant and see what happens. So we get secant of theta times sine of theta plus secant of theta times cosine of theta. Okay, this is not quite obviously the right-hand side yet, so let's keep playing with it. Well, we know that secant is 1 over cosine, and it's often a good idea to write things in terms of sine and cosine, as we saw in the last section. So let's write secant times sine as sine over cosine, as we just did. And secant times cosine, you may recognize that right away as 1, but you could certainly write it as cosine of theta divided by cosine of theta, because secant is 1 over cosine of theta. Okay, and remember, we're trying to arrive at 1 plus tangent of theta. Well, this is great news, because sine of theta over cosine of theta is indeed tangent of theta, and cosine of theta over cosine of theta is, of course, equal to 1. So we have arrived at the right-hand side. So that completes the proof. That's it. So again, at no point did we actually write down the identity we're trying to prove. To prove an identity, you always start with one side, and through a chain of equal signs, you keep simplifying or applying the rules of algebra in whatever way seems suitable to you until you naturally arrive at the right-hand side at the end of that chain of equal signs. And that's how you prove an identity. All right, let's verify this particular identity. So again, we can choose any side to work with, but very strongly recommend you pick the more complicated looking side, which in this case is, I think, quite clearly the right-hand side. So right-hand side, let's write it down. Okay, and again, at no point will we write that this is equal to cosecant squared, because we are never going to write the identity down in our proof of the identity. Okay, well, just follow your nose algebraically. What do you want to do with this thing? Well, we have several options. One is we can distribute the cotangent squared. So yeah, let's do that. So cotangent squared times 1 plus cotangent squared times tangent squared. Now always keep in mind what form you're trying to end up with. We want this thing to become cosecant squared. So what can we do to turn this into cosecant squared? If you think about the fact that we have the identity one coat in the closet. We can take advantage of that if we can turn this form here into 1 plus cotangent squared. And we've got the cotangent squared. So really we just need to ask ourselves, is this thing here equal to 1? And of course it is, because cotangent times tangent is 1. So cotangent squared times tangent squared is 1 squared, which is 1. All right, so cotangent squared plus 1, well, that's the one coat in the closet identity. So this is cosecant squared. And that is the left-hand side. So we're done the proof. Again, this is a proof because it is a sequence of obvious steps. Every single step in the proof is obvious from the one before it. And when you put them all together, you get a chain of equalities connecting one side of the identity to the other side. And that's why this counts as a proof. Okay, I want to revisit this example and this time just show you that there's really not always just one right way of proving a trigonometric identity. For instance, again, starting with the right-hand side, we could have noticed that 1 plus tangent squared is secant squared. So this would give us cotangent squared of x times secant squared of x. Okay, and while it's not quite obvious that that's cosecant squared yet, if we now turn everything in terms of sines and cosines, so cotangent is cosine over sine, so cotangent squared would be cosine squared over sine squared, and secant is 1 over cosine, so secant squared is 1 over cosine squared. Now you can see that we get 1 over sine squared, and that is indeed cosecant squared of x, which is the left-hand side. So we win, of course. But this was a very different way than the way we approached it the first time we did this example. So again, there's not like one right way to do it. Just follow your nose, right? Just do what sort of makes sense. Keep in mind what you're trying to get at. In this case, we wanted to get at cosecant squared. So yeah, as long as you're not breaking the rules of algebra and trigonometry, one way or another, it should be possible to arrive at the form you want. All right, so here we are going to verify this identity. And once again, we're going to choose the more complicated looking side to work with. Now, it's not really that clear which side is more complicated than the other. So in some situations, you just want to choose the side where you at least have something you can try right away. For instance, on the right side, we can try foiling that, right? So we know if we foil that, that's a thing that we can do and it will do something. So we'll end up somewhere, right? And then maybe we'll end up somewhere where it becomes obvious how to finish. If we were to start with the left-hand side, which I don't think is a great idea, but if we were to start with the left-hand side, keep in mind that we would be starting with tangent squared over secant squared, and through a chain of equalities, somehow we're supposed to end up with this. Now, in order to get this final form, that means that somewhere along the way, probably toward the end, we would have had to start factoring, because this is a factored expression. And that's not to say that factoring is not a thing that we might need to do sometimes, but it's a lot easier to FOIL and expand than it is to factor, right? I think we can all agree on that. So if there's a direction we can do the work where we're not factoring, let's try and choose that direction at least. So I vote we work with the right-hand side. And of course, we're going to start by writing down the side that we're working with. So that would be the right-hand side in this case. Okay, so let's just follow our nose. We're going to FOIL this guy. Okay, well this is the difference of squares. We have 1 plus a thing times 1 minus a thing, so that would be 1 minus the square of the thing, right? So it's like a squared minus b squared. So we get 1 minus cosine squared of t. All right, and hopefully you are starting to recognize the forms of the Pythagorean identities. 1 minus cosine squared is in fact sine squared. Okay, and how do we know that? That's because we know the form cosine squared plus sine squared is equal to 1. So if you just subtract cosine squared from both sides of this identity, you're going to get sine squared by itself. All right. Now remember, we're trying to get tangent squared over secant squared, and we have arrived at sine squared. And there's really nothing obvious that comes to mind for me that we could do to simplify sine squared even further and somehow magically arrive at tangent squared over secant squared. Now, when it happens that you're working on a proof and you arrive at something very simple, like we just did here, sine squared of t, the recommendation is that you actually stop working on the right-hand side. You now, elsewhere, start a new thread of work, and we're going to go with the other side, the left-hand side. And we're going to follow our nose with the left-hand side. And we're going to hope that we arrive at sine squared of t. And if we do, then we can deduce that the two sides are equal because they both simplified to the same simple expression. Okay, so what can we do with tangent squared over secant squared? Well, let's write everything in terms of sines and cosines because something's probably going to happen. So tangent is sine of t over cosine of t, and this is all squared. Actually, why don't we write it as sine squared of t over cosine squared of t. And this is all over, and let's keep track of the hierarchy of fraction bars here. So that fraction is divided by secant squared, which is 1 over cosine squared t. Okay, so very good. We can now clear this fraction within a fraction situation by multiplying the entire numerator by cosine squared and simultaneously multiplying the entire denominator by cosine squared. So what we're going to get is in the numerator, these two factors cancel, giving us sine squared of t. And in the denominator, these two factors cancel, giving us just 1. So of course, a thing over 1 is just that thing. So we have reduced to sine squared t. And you can see that both the right-hand side and the left-hand side independently reduced to the same expression. That proves the identity. That proves the original left hand and the original right-hand side are equal to each other. Okay, and let me emphasize again, at no point did we blend the right and left-hand side work, right? This was completely independent of this part here. And at no point did we equate the left-hand side and the right-hand side, as you're not allowed to do that in a proof of a trigonometric identity. Okay, let's verify this interesting looking identity. First of all, let me remind you that at no point are we allowed to equate the identities. So this particular identity really tempts us to do that because it looks like if you just cross multiply, you're going to get something really clean out of this. And that's true, actually you would. But that's an illegal move because we are not allowed to set these two equal to each other, not until we've established that it's an identity. And the whole point of this exercise is to establish that it's an identity. So that's just not allowed, unfortunately. Okay, so what we're going to do is what we've been doing. And so we have no choice but to do that, which is to start with one side and work with it and hope that we arrive at the other side. So now, it's not clear at all which side is more complicated than the other. So in a situation like that, you just pick a side and start working with it and hope that things happen. So let's start with the left-hand side. All right, so what can we do to this thing? Well, it's not terribly obvious, but one thing we can always do is write everything in terms of sines and cosines and just see what happens, right? So secant is 1 over cosine of x. Tangent is sine of x over cosine of x. And sine of x in the denominator is already written in terms of sine and cosine, so we'll leave it alone. So we now have a complex fraction, a fraction within a fraction. So let's clear that by multiplying everything by the mini denominator here. That would be cosine of x. So we're going to go cosine of x, cosine of x. So in the numerator, this cosine distributes to 1 over cosine, giving us 1, plus here cosine of x distributes into this guy, giving us just sine of x because the cosines cancel. And in the denominator, we simply get sine of x times cosine of x. All right, it's not at all clear how this is supposed to turn into the right-hand side, but what we can do is leave this alone and go to the right-hand side and turn everything there into sines and cosines. And let's just hope that in doing so, we get exactly this form. The right-hand side is cosecant of x over secant of x minus tangent of x. And yeah, let's turn everything into sines and cosines. So cosecant is 1 over sine of x. And this is all over secant, which is 1 over cosine. And tangent, which is sine of x over cosine of x. Okay. So again, we have the problem of fractions within fractions. We should deal with this. And the way we're going to do that is by multiplying by the common denominator among these little mini fractions. So here the common denominator will be cosine times sine. So we're going to multiply everything by cosine times sine. Cosine times sine. In the numerator, this sine factor cancels with that sine factor, and we get cosine by itself. In the denominator, this cosine times sine distributes into this term, where the cosines cancel, and we're left with a sine of x. And the cosine times sine distributes into this term, where the cosines cancel, and we're left with sine squared of x. Okay, so after turning both the left-hand side and the right-hand side independently into sines and cosines, they didn't quite reduce to the same thing. And it's not obvious how to turn one into the other. So, all right, let's keep working with the right-hand side. What do we want down here? We want this to be sine times cosine down there, ideally, at the end of the day, right? So that it matches the left-hand side. So, all right, well, we can at least factor a sine out. So we can see cosine of x, sine of x times 1 minus sine of x. Okay, well, what do we want down there? We want this to be sine of x times cosine of x. So that means we need to find a way to turn this into cosine of x, right? Well, if it were 1 minus sine squared, let's just pretend for a moment that we had 1 minus sine squared. We'll just put a 2 there. Of course, there isn't a 2 there, but let's put 1 there. Now it's 1 minus sine squared, which of course is cosine squared. And that's great. I mean, that's sort of closer to sine times cosine than what we've got. However, we don't have that squared there, so we can't just do that. But what we can do is multiply the top and the bottom here by 1 plus sine of x. Because what we've done is we've manufactured an a minus b times a plus b situation, which is a difference of squares. So what we have is cosine of x times 1 plus sine of x. This is over sine of x times, if we FOIL out this difference of squares, we're going to get 1 minus sine squared of x. All right, well that's cosine squared of x. 1 minus sine squared is cosine squared. Great, we have things we can do now. Look, the cosine factor that's right here cancels with one of the cosine factors from the denominator. So we're going to get 1 plus sine of x in the numerator divided by sine of x times cosine of x. And that is exactly the same simplified form that we arrived at when we worked on the other side of this. So that's it. We are done. We have proved the identity. Right. Let's try and verify this one here. I think unambiguously we can all agree that the left-hand side is the more complicated looking side. So let's dig in. Our first move is to simply write down the side we're working with, in this case the left-hand side. Okay, so we have two fractions here. We should probably try to combine them to a single fraction, but they have different denominators, so we're going to need a common denominator. Well, that would just be secant theta plus tangent theta times secant theta minus tangent theta. So this first one here needs to be multiplied by secant theta minus tangent theta in order to create that common denominator. And the second term needs to be multiplied by secant of theta plus tangent of theta over secant of theta plus tangent of theta in order to create the common denominator on that fraction. So what we're going to get is here we have the new numerator here will be secant of theta minus tangent of theta, and this is over secant of theta plus tangent of theta times secant of theta minus tangent of theta. And for this other one, we have secant of theta plus tangent of theta over secant of theta minus tangent of theta, secant of theta plus tangent of theta. Okay, well, at least now we have a common denominator, so we can write this as one combined big fat fraction. So we have in the numerator secant of theta minus tangent of theta plus secant of theta plus tangent of theta, and in the denominator secant of theta plus tangent of theta times secant of theta minus tangent of theta. Okay, so in the numerator we have negative tangent of theta canceling with positive tangent of theta, and secant of theta plus secant of theta accumulate to 2 secant of theta. And in the denominator, we can FOIL. Again, we have a difference of squares situation. We have a plus b times a minus b, which is going to be a squared minus b squared. So this is going to be secant squared of theta minus tangent squared of theta. Okay, well, secant and tangent play very well together in the I tan secretly identity. We know that 1 plus tangent squared is secant squared, right? I tan secretly. So what is secant squared minus tangent theta? Well, we could build that by moving the tangent squared to the right-hand side there. We'd get 1 is equal to secant squared minus tangent squared. Oh, excellent. So this whole denominator is just 1. So this is 2 secant of theta divided by 1, which is, of course, 2 secant of theta. And lo and behold, that is the right-hand side of the identity. So we win.